Okay, so in this class we're gonna discuss Kirchhoff's rules, and we're gonna solve an example on using Kirchhoff's rules. As I said last time, Kirchhoff rules, they're very, very powerful. Okay, they can help you figure out everything you need in a very complicated circuit. Okay, so if you need the voltage, current, power, or anything of a single element in a circuit with like 100 elements, okay, it can help you find these things without drawing all these diagrams, without simplifying the diagram, okay, which is very powerful, okay. And also it applies not only to resistors, it also applies to capacitors we learned before, and then also the inductors we're gonna learn in magnetic field, okay. So I always say that Kirchhoff's rules is my favorite theory in physics too, okay? Because it's very, very easy to set up, okay? Once you set it up, then you just do the algebra. But the algebra can be lengthy. You may still need to spend a lot of time doing the algebra. But you wouldn't be, you know, looking at this circuit and then don't know what to do with this circuit, don't know where to start or how to set up this problem, even if the circuit really complicated, right? And you don't need to draw new diagrams, okay? So that's why it's my favorite theory in physics too. So let's take a look at these two rules. So the junction rule is the total current into a junction must equal the total current leaving the junction, okay? And the other rule is called loop rule. The sum of the potential difference around any closed loop must be 0, okay? If we read these two rules, well, it may not be that straightforward to you, okay? That's what I usually say, okay? We don't need to do a lot of reading in physics. We don't have reading assignments in physics, right? You don't need to read these laws like 10 times, 100 times in order to understand them, in order to get a new understanding. You don't, right? You just do the math, you practice, you solve real problem, then you know what these rules mean, what these laws mean, how to apply them in real life. So let's take a look at these rules in real examples, what they mean, okay? So let's first discuss junction rule. Junction rule is the easier one, okay? So the junction rule says the total current into a junction must equal to the total current leaving the junction. So so that's how I would like write it in an equation. Okay, if there's a junction, you add all these currents together, you get a 0. Okay. Now let's use a real junction. Okay, in a circuit, then we know how to use this rule. So say if you have a junction like this in a circuit, a junction is where there are multiple currents, not just one current, right? The current splits, the currents merge at that point. That's called a junction, okay? The junction is not always a corner, okay? If you see a corner like this is not a junction, okay? This is still the same current, right? You don't have different currents here. That's just a corner we draw, and that's like a right angle we draw in a diagram to make it look nice, right? I always tell my students, when you see a circuit like this, right, and then you see a diagram like this, I want you to connect this circuit for me, okay? You're gonna use these wires and then connect the circuit. Do you really need to make a right angle here? No, you just need to use one wire to connect this end to this end of this resistor, and that's it. See that this is one path, right? Nothing split. This is only one current, so this is not a junction, okay? This is a corner we draw, okay? A right angle we draw to make this diagram look nice, okay? This is a junction, right? Because I have 3 different branches. Okay, so I should have 3 different currents, right? So if I call this current I1, and this current is different than this and this, right? None of them are going to be equal, okay? And this current, I say, if I call it I2, and then this one, there's another current I3 down, okay? So obviously, intuitively, you know that, okay, whatever like happens in the circuit, everything other places, I1 goes this way, and then you see it splits up into I2 and I3, right? So obviously, I know that I1 is going to be equal to I2 plus I3. That's intuitive to me, right? So, and then if this guy is like 11 amps, right, and this guy is like 7 amps, so I can actually calculate I3 must be 4 amps, right? So that's why this is always a relation among these currents at one junction, right? Even if I have 10 currents coming at a junction, that must be true, right? All the current entering this junction must be the total current leaving the junction, right? Because the charge is conserved, right? They're not going to disappear, right? So, but when we use this junction rule, we usually don't do this, and if you want to do total current entering equals total current leaving, you're going to first count how many. You're going to be very careful. You're going to pick all these currents entering this junction, put them on one side, and then you're going to have all these currents leaving the junction. You can count all of them. You're going to make sure put them on the other side. Okay? If there are many currents, sometimes you may make a mistake, or you may miss one on the left or on the right. So what we usually do is this. We're going to list all the currents on the left-hand side. So I'm just going to count, okay, there's 3 currents, I'm going to put them on the left-hand side, okay? So I'm not going to miss any current. But I'm going to assign them correct signs, right? So to distinguish entering and leaving, okay? That's what we usually do in physics, right? How do we distinguish left and right, up and down? We assign them signs, okay? So then our convention is this. When a current is entering the junction, we call it positive. And then if a current is leaving a junction, we call it negative. Again, you can do it the other way around, okay? As long as you stick to the convention you use, okay? So in this case, if I see a junction like this, I have to write down I1, I2, I3. I'm going to add them. I get a 0, right? But then I'm gonna put all these currents on the left, but I'm going to assign them the correct signs, right? I1 entering, okay, my convention is entering positive, so positive. I2 leaving, so I'm going to assign a negative sign, right? What about I3? I3 leaving, I'm going to assign a negative sign. Now I have listed all the currents on the left with their signs. They must be equal. The sum of all these currents must be equal to 0. So that's how I'm going to use the junction rule, right? List all the currents on the left-hand side with the correct signs and equal them to 0. Okay, all right. So you can apply this rule to any junction you find in a very complicated circuit. So they may give you many equations, right? So once you get these equations, you just solve this equation. You just do algebra without this circuit anymore, right? You do algebra, you can find these currents. So this junction rule, okay. I hope this is intuitive. Now the second rule is called the loop rule. So let's take a look at the next slide, the loop rule. So the loop rule says the sum of the potential differences around any closed loop must be 0. So that's actually a conclusion from conservation of energy, right? Because if you go around the loop, you come back to a point, the potential energy must be the same, right? And if the potential energy is the same, so the sum of the potential differences, the voltages must be 0, okay? Because you're back to where you start, okay? Now, that's how I would write this guy in an equation, okay? If I pick a loop, I add all the potential differences or voltages in this loop, I should always get a 0. So now, again, let's take a look at a real loop so we know how to apply this rule. So that's the loop in this slide 17. Now if there's a battery and then 3 resistors, okay? So this guy has a voltage, we call it V battery, right? And then this guy is going to have if this is R1, R2, R3, this guy is going to have a voltage V1 on it. This guy is going to have a voltage V2 on it. This guy has a voltage V3 on it. Okay? So, and then you're gonna put all these voltages together on the left hand side around this whole loop, you equal them to 0. So you will get V battery minus V1 minus V2 minus V3 equals 0, right? Okay, and then that's how we apply the loop rule. You just write the sum of every voltage around a closed loop, and then you're going to equal the sum to 0. And you see that if you rearrange this equation, what do you get? You put all these three V's to the right, you get the voltage from the battery equals V1 plus V2 plus V3. Of course, this is a theory for a series circuit, right? If there are three resistors connected in series to a battery, each of them only gets part of the voltage, and then if you add all this voltage together, you get the total voltage. Okay? So that agrees with the series theory we discussed earlier. Okay? Then you may ask, okay, now if you tell me, okay, let's not use this, okay, let's just always use this loop rule, write all the voltages on the left and equal them to 0. But why is there some positive signs and negative signs, right? How do I decide which one I should call positive, which one I should call negative? Why don't I just add all these numbers together, right? Well, first of all, if you add all these numbers together, you shouldn't get a 0, right? Because you're gonna have a positive number, positive number. You add some positive number, you never get a 0, right? So that's why we still need to assign them the correct signs, like what we do with the junction rule. But how do we assign them the correct sign? So that's what we're gonna discuss next, okay, on the next slide. So we're gonna use the fact that the voltage, when you cross, so you're gonna imagine you travel around. So this is a shortcut, again, it's a shortcut, okay? You imagine you travel around the loop. You can start from any point, okay? You can travel in any direction. Well, usually there are just two directions, right? Either you travel like counterclockwise or clockwise, okay? You start with any point you like. You travel in any direction you like. But you're gonna make sure that when you're traveling, you write down the voltage of every element you see in this loop until you come back to where you started, okay? Then you have completed this loop, you put a 0 on the right. Then how do I decide, so I know how to write down the voltage. How do I decide the sign, right? Like here, of each voltage, right? Okay? So take a look at the rules at the bottom, okay? So the ground rule is this, okay? You are going to determine when you cross an element, does the potential difference, does the potential go up or go down, okay? If you cross an element, the potential goes up, okay, you put a positive sign there. If you cross an element, the potential goes down, you put a negative sign there, okay? That's how you figure out the sign for each voltage, okay? All right, so that's a rule. But again, let's see how we can apply that to different elements in a circuit. For a battery, okay, a battery is easy. If you see a battery in a circuit, right, in a closed loop, and you're crossing this battery, okay, but you may cross this battery this way or the other way, totally depending on in which direction you're traveling around the loop, right? You imagine you are traveling the loop. You write down the voltage for every element, okay? A battery has a definite negative and positive terminal, right? The symbol is this, right? The short line is the negative terminal. The longer line is the positive, right? So, and that means the short line, the negative terminal is always at a lower potential. The positive terminal is always at higher potential, right? That's intuitive. That's why we call them positive and negative, right? You're not going to call a higher one negative and a lower one positive. That's counterintuitive. People are not going to like that. So then you see that if you cross this battery this way in a loop you're traveling, you're going to first write down the voltage say maybe it's like 5 volts or something, the problem. It gives you, you just write down 5 volts. Or if it doesn't give you, you just write this symbol there. That might be a variable you're going to solve at the end, okay? Then the sign, you see that if you cross the barrier this way, you're going from negative terminal to positive terminal. You're going from a lower potential to a higher potential. You're climbing up. So you're increasing the potential. The potential increases, right? So you're adding potential. So you put a positive sign. So that's going to be the term you write down in that loop equation, okay? So it's pretty much like this. When I travel this way, clockwise, I start from this point A, say, okay, and B, C, D. I start from this point, I travel and I cross this barrier, and I go from negative terminal to positive terminal. So that's why the voltage for this barrier is going to be a positive value in my loop equation, okay? So say you have a barrier in a loop. Now you're traveling in this loop, but you're crossing this barrier in this direction, okay? Still, the barrier is going to have a voltage for sure, right? The problem may give you, or you just write it down, or if it doesn't give you, you write this symbol in the equation, you can solve for that, right? Now, if you cross a barrier this way, in a loop, you decide to travel in a loop like this, and then you see a barrier at the bottom, you're going this way, right? So again, it doesn't matter how you travel, okay? But if in a case you're crossing a barrier in this way in your loop, you want to write down the voltage of the barrier in the loop equation. You can write down the voltage, either the symbol or number. Now you're going from positive terminal to negative terminal. You're going from higher potential to lower potential. You're going down. You're going down. You're decreasing the potential in this loop. So you're going to put a negative sign in front of this voltage, either the number or symbol. So that's going to be the term you write down for the battery, okay? So for a battery, it's actually easy. You only take a look at these two lines, the positive or negative terminal, and then see if you're going from positive terminal to negative, or negative terminal to positive, right? So you know that if you're going down or you're going up, so that's going to help you get the sign, right? If you're going up, you're increasing the potential, I'm going to put a positive sign in front of the voltage. If I'm going down, I'm decreasing my potential, I'm going to put a negative sign in front of this voltage for the battery. So that's the rule for a battery, right? Now for a resistor, okay, so let's see. For a resistor, because a resistor doesn't have a positive or negative terminal, doesn't have a definite higher or lower potential, so you're going to decide the higher and lower potential using the current, okay? So if you have a resistor, okay, all right, you have a resistor, and then say the current is going this way in this resistor. There is a current, okay? So this is part of a loop, right? So there must be a current going in this resistor, right? If there's a current going this way, okay, and then you're traveling, okay, remember you're traveling this way, because you always travel in this loop in a certain direction, you write down the voltage for each element, right? Then the higher and the lower potential of each end is going to be determined by the current. Okay. Then how is it determined by the current? Think of a current as water. Okay. So the water, due to gravity, okay, the water always flows up here or downhill due to gravity without any other external force. Naturally, water is going to always flow downhill, right? Water is always going to flow from a higher potential to lower potential. So imagine current is like water in a circuit. So current always flows from higher potential to lower potential. Current always flows downhill, okay? So if there is a loop and this circuit is in there, or this resistor is in that loop, and then I figured that there's a current going this way on this through this circuit. So that means this end, it's going to be higher than that end. That's why current is going to go this way instead of that way, right? So you can sort of, like, if you like, you can draw it this way. So the current goes downhill, right? The current goes downhill. So I can say this end must be higher than this end. Okay, the potential at this point is going to be higher than this potential. Okay? Now you see that if you are traveling, you're traveling in this loop, but you're traveling in this direction. Okay, say this is a big loop. Now you're traveling starting from some point and then you come across this resistor. You're traveling this way, but you realize the current going down, right, that way. Okay, so that means you see that I'm traveling from a negative potential from a lower potential to a higher potential. So the voltage, the potential difference I write down in this equation should be the voltage of this resistor. Either it's a symbol, it's or a number the problem gives me, right? And in this case, I'm traveling uphill, right? So I should have a positive sign here. I'm climbing up, right? Because water always flows downhill. I'm climbing up. But the diagram doesn't have to be like this, right? The diagram can be like this, you know. Okay? So you don't need the problem to draw this guy like that. Okay? The problem can also draw it this way. The current goes this way. If the current goes this way, if the current goes that way, this is always higher potential, this is always lower potential. Okay? All right? So don't be confused by the diagram. Okay? You just need to take a look at the direction of the current. You know which end of this resistor is at a higher potential or lower potential. Okay? So that's what you do with this resistor. When you see a resistor like this and the current goes through in that direction, and then you're traveling opposite to you're traveling against the current, you are climbing up, right? If you're traveling against water flowing downhill, you're going uphill. So the voltage you write down for the resistor, it's going to have a positive sign. Okay? Now, what about if you still see a resistor in circuit? Okay, it doesn't have to be horizontal, right? It can be any orientation. And then the current is still going this way. You see it? And then, okay, then I know that the current is like water. It always flows downhill. It always from higher potential to lower potential. So it's always going to be like this. So this end has a higher potential than that end. And then if you are traveling in a loop and then you see this resistor, right? And then somehow you're also traveling in this direction. This is the direction of traveling, right? Say this is a big loop. You travel, and then you see this element. You're traveling through it in the same direction as the current. Now, if you're traveling this way, you see that then pretty much, if I write it this, if I draw it this, so maybe easy to understand. I have this current going this downhill, right? And then I'm also traveling in this direction with the current. So I'm also going downhill. I'm also going from high potential to low potential, right? So the term I write down for this resistor, it's going to be the voltage with a negative sign, because I'm going downhill, the potential is decreasing. Okay? So that's how you find the correct sign for the voltage of a resistor, right? Now you can see, take a look at this R1, R2, R3. First of all, if this is a battery, this is negative terminal, this is positive terminal, so the current definitely is going to flow this way, right? And then you see that the battery voltage, I wrote it down positive because I'm going from negative terminal to positive. A battery has a definite positive and the negative terminal. Okay, you don't need to worry about the current. When you see a battery, right, you see that you never need to worry about the current. You only take a look at these two terminals. Then you know if you're traveling uphill or downhill. You know how to assign the correct sign for the voltage. But when you see this R1, right, so I'm going to write down this V1 here. But do I put a plus sign or minus sign here? Take a look at the current. The current is going this way, right? But I'm also traveling this way, right? I'm also traveling clockwise. So this is how I'm going to cross this barrier. So I'm crossing this resistor. I'm crossing this resistor in the direction of the current. So I'm crossing the resistor in the direction of current. I'm crossing the resistor in the direction of current. I'm going downhill. So that means I'm going to place a negative sign here, right? And then you keep traveling, you see R2, right? I'm traveling this way. The current is also going this way. So this is downhill. This is downhill. So I'm going to put a negative sign because I'm still traveling from higher potential to low potential. Okay, so I need a negative sign. Then I keep traveling, I see this R3, I will write down the voltage for R3, and then you see that I'm still traveling this way, and the current also goes this way from the battery. So I'm traveling with the current, I'm traveling with the current, I'm traveling with the current, I'm still going downhill because the current always flows downhill like water. So I also still need a negative sign for the voltage of R3. Then you see that we can, then I'm going to be back to where I started. If I started from A, so I have already written these 4 voltages I see in this closed loop. I'm done on the left hand side, I put a 0 on the right hand side. That's the complete equation for this closed loop. Okay, so this is how we use this setup loop rule. It's a little bit more complicated than the junction rule, okay? But again, just follow all these rules we set up, okay? You can always get the right equation with the right signs, okay? And then there's a number of the times, there's a limit on the number of times you can use each rule, okay? So take a look at this slide at 19. Because there may be like many junctions in this circuit, right? So in principle, you can use every junction to set up a junction rule. You will get a bunch of equations, right? But sometimes you will get the equations, okay, the same as the one you already wrote down, okay? So how do I know that I write a new equation using a junction, okay? In order to get a new equation, you need to include at least one new current when you pick a new junction. So say there are like 10 junctions in this circuit. I already used the 5 junctions to write down 5 equations. And then when I use the 6th junction, I want to write a new equation. But I realized all these currents in that junction, okay, have been already used in these 5 equations I just wrote down. That means if you write another equation for the 6th junction, this is not considered a new equation, okay? So you shouldn't use junction 6 to write an equation because that's not going to be a new equation, all right? And loop rule, there's also a limit of the number of times you can use a loop rule. Every time you use a loop rule, you want to set up a new equation, you should include at least one new element, okay? If you don't include a new element, then it's not going to give you any new information. It may look differently than the equations you already got from other loops, okay? But if you rearrange it, okay, it will be identical to one of the equations you already set up. So it's not going to give you a new equation, okay? Again, if you read them, even if you are listening to me, these 2 rules are a little bit confusing to you, okay? What do you mean there's a limit on this number of times using these 2 rules? Let's take a look at a real example so you see what I mean. You know how to apply these rules, and you know how many times you can use a junction rule and loop rule in order to get new equations, okay? Physics doesn't require a lot of reading. You read this slide, you read these 2 sentences 10 times, you still don't know what they mean. But practice, do an example, do the math, you understand that. So that's what we're going to do. Let's take a look at the last slide. So this is really a complicated circuit. So let's draw it. So we're going to use Kirchhoff's rules to find everything, pretty much everything on this circuit, okay? So I'm gonna first draw this circuit. All right, so that's the left. All right, I believe I have got everything. Now let's write all these numbers. So this is 15 ohms, 24 volts, 0.75 ohms, 0.5 ohms, volts. Okay, I believe I have got everything. Let me double check. Okay, now we want to solve this circuit, right? So we want to find the 3 currents in this circuit. So, okay, the problem already labeled 3 currents for us. This one is called I1, and then this one is called I2. And then the current in the middle is called I3. Okay, so that is a junction, right? You see that there are 3 currents at this point, so that is a junction. So the problem also labeled all these points for us. Okay. So if the problem doesn't label these points, I will label all these points. Okay, why? So that I know which junction I'm working at, which loop I'm working at. All right, so now let's see. Let's apply. So I want to find these 3 currents, and this is really a complicated circuit. You can't even use the parallel and series to simplify this circuit, okay? Because there are so many batteries here. We never learned how to combine resistors with batteries, okay? How do you simplify these 2 guys? How do you combine these 2? There's so many batteries, right? Even if I want to do parallel series, draw a bunch of diagrams. You don't know how to combine resistance batteries, okay? So you can't even do that way, even if you want to do it the hard work. But we can use Kirchhoff's rules. We don't need to draw any new diagrams. We don't need to simplify it, okay? I'm just going to use this original diagram, okay? I'm just going to set up equations and do algebra, okay? All right? So I'm going to use junction rule, okay? So when I use junction rule, I'm going to write down which junction I'm working at, okay? To remind myself, okay, I'm working on this junction, don't make any mistakes. Just write down all the currents at this junction. Now at this junction, there are 3 currents. The problem already labeled these 3 currents here for us, and also labeled the direction. I want it this way, I2 this way, I3 this way. So I'm using our convention, I1 positive, right, entering, I2 negative, leaving, I3 negative, leaving. Okay, then that's it, 0, right? So then you would say, okay, I'm done with this junction. If there's another junction, I can set up another equation, right? Because I have 3 unknowns here. I need at least 3 equations to solve them, right, mathematically. So I need 2 more equations, okay? So let's see if I can use another junction to set up a junction rule, okay? Is A a junction? A is not a junction, okay? It's a right angle we draw in this diagram, but this is only one path, right? If you connect these 2 resistors in real life Do you have to make a right angle with the wire? No, you don't, right? If you do that, people are gonna laugh at you, right? This is a schematic. So all you need to do is just use a wire, connect them. So this is not a junction, it's still one path. The current doesn't split, doesn't merge, the same current. So C is not a junction, right? D is not a junction. E is a junction, right? You see there are 3 currents here, F is not. So there are actually only 2 junctions here, B and E, okay? So, okay, but at least I can write another junction equation for junction E, right? So let's see. You may think there are 3 different currents here, but these 3 currents are the same currents we just listed. Because, you see, this is one path, this is one path, this is one path, okay? We draw a right angle here, okay? We turn around here, but that's because we want to make this diagram look nice. When you connect this circuit in real life, you just need to connect this to this, to this, to this in one path, right? So this is the same path. So this is I1, the same I1, the same I1. If you call it I1, I1, right? This is one path, this is one branch, okay? So you see that this current is going to be I1. Now this current, the middle one, you see, this is I3, this is I3, this is I3, this is I3. There's one path. This is only one current in this whole path, okay? Now, what about this one? Well, then you see, okay, this is I2. This is also I2, okay? This is also I2, 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 I2. Now you see that the 3 currents at junction E is going to be the same 3 currents I used for junction B, right? But now I still want to set up an equation for that. So let's see. If I set up a junction equation for this junction, what do I get? I will get I3 entering, I2 entering, right? And then I1 leaving. Okay? So you may think, oh, I got 2 equations, nice. I only need to find a third one. Compile these 2 equations, right? If I move these 3 terms to the right, what do I get? I would get I1 to the right becomes positive, I2 to the right, negative, I3 to the right, negative. Look at these 2 guys. They are identical, they are the same, exactly the same. So that's what we meant. If you want to use junction rule for a different junction, okay, then the junction you have already used, you have to at least include one new current, okay? Otherwise, you're not going to get a new equation. You will get an equation which is going to be identical to one of the equations you already got, okay? Or it's going to be the sum or difference of the sum of the equations you got. So it's not going to be considered a new equation. It's not going to give you any new information. You're not going to be able to solve that equation, use that equation to solve all these unknowns, okay? You see that I use the junction E, I set up this equation. All these currents I used have already been used at this junction B. So this is not going to be considered, it's not going to count as a new equation, right? It gives me the same information. So they're going to be counted as one equation. No, okay? You don't get 2 equations, you only get 1, okay? So that means junction E, if you have already used the junction B, junction E is going to tell you the same information, okay? So you don't use that, okay? So I only have 1 equation. And there are only 2 junctions, so I'm done with junction rule. I'm going to move on to loop rule. But if I set up Kirchhoff's rules, I always set up junction rule first, because junction rule is easier than loop rule, okay? Now we're going to set up a loop rule, okay? Now let's see. How many loops are there, okay? You're going to pick a loop and set up the loop rule one. 1, 2, only 2, 3. The big one is also a loop. So you have 3 loops in total in this problem. But you only need 2, right? I already have 1 equation. I only need 2 more equations to find I1, I2, I3, okay? So you can pick any two of them out of these three, right? You will get the right answer, okay? Say, I'm just gonna pick these two small ones. I'm gonna travel clockwise, okay? So again, if you like, you can travel counterclockwise. You can start for that point, there's nothing wrong. You always get the same equation if it's the same loop. Now let's start with this loop. So I'm gonna always write down the loop name with all these points to remind myself I started with this point. I'm gonna go through all these points, go back to the point I started. Don't miss anything, okay? So I'm gonna start with the loop on the left. So that's loop A, B, E, F, A. Okay, this is a complete loop. See, I'm back to A at the end. Now I'm gonna write down, I'm gonna start from A, go to B, go to E, go to F, go to A, and write down the voltage for each element. Okay, so let's start from A. Okay, and now I'm gonna go to B. Okay, I see a resistor. So I'm gonna write down the voltage of this resistor. In this case, I don't have the number, but I can write an expression which is going to be I1 times 20 ohms, right? So I have I1 there, and that's good because I want to solve for I1 at the end. Now, what about the direction? You need to take, what about the sign? You need for resistor, remember what we said, you need to take a look at the direction of the current. The current always goes downhill, okay? So the current is going this way, so that means this is downhill. This is lower potential. I'm also traveling this way, see? I'm traveling this way. So I'm going with the current when I see this resistor. So I'm going downhill with this resistor, with the current. So my potential decreases, negative sign, okay? Now let's keep going. Now I'm traveling this loop, so I don't go to the B, don't go to C, I want to go to E. Now I'm gonna write the voltage one by one. This guy, what is the voltage? I don't have the number, but I can still write it as the current times the resistance. Now the current is I3 now, right? And it's good. I want to include I1, I2, I3 in all these three equations. Now what about the sign? Now take a look at the current, direction of the current. I3 goes down, right? So I'm also traveling this way. Remember, I decide to travel clockwise. So when I see this element, I'm going down, right? I'm traveling this way. So I'm traveling with the current. I'm going down here again, okay? It's not because I'm going in this down direction on this diagram. It's because I'm going with the current, okay? Now, okay, I'm done with this guy. Let's keep going. Now let's see, now we see this 3-volt battery. For battery, forget about the current. I don't even need to look at the current, right? I just need to look at these two terminals. So I'm traveling this way, so I'm going from the negative terminal to the positive terminal, right? So I'm going to write down 3 volts, and then I'm traveling from lower potential to higher potential through this battery. So I'm going up. I'm gaining some potential. Positive. Okay? I don't need to worry about the current. When you see a battery, forget about current. Only look at these two terminals. You know if you're going uphill or downhill. We're done with the battery. Keep going. Now I see a resistor. Okay, resistor, you need to take a look at the current. But first of all, the current, the voltage is going to be I3 times 0.25. Right? Okay? So, and then what about the sign? I'm still traveling with the current. Current goes this way. I'm also traveling this way. I'm going downhill with the current. Negative sign. Okay? Now keep walking. You don't go that way because I'm walking in this loop. Now I see this 15 ohm resistor. 15 ohm resistor, okay. I'm going to write it down. But the current becomes I1 again, right? So it's going to be I1 times 15 ohms. All right? So what about the sign? Take a look at the current. The current is going that way. I'm also traveling that way. So I'm traveling with the current again. The potential goes down. I'm traveling downhill with the water. Negative. Now keep walking. Now I see a battery. Okay, when I see a battery, forget about the current. Take a look at these two lines, right? I'm going from the shorter line to the longer line. I'm going from negative terminal to positive terminal. I'm climbing up. I gain some potential when I cross this battery. Okay, so I'm gonna write down plus 18 volts. Okay, I'm done with this guy. Now keep walking. Now I see this resistor. This resistor, what is the current? The current is I1, but resistance is 0.5. That's how I would write the voltage. What is the sign? The current goes that way, okay? I'm still traveling with the current. I'm going downhill. You see that? It's not because I'm going down on this line, on this diagram. I'm going downhill with the current, okay? So that's still negative. All right, now I'm back to A. I already finished the loop. Put a 0 there. Okay, so that's going to be the second equation I get. All right. Now I still need another one. So I'm going to pick the loop on the right. So that's loop B, C, D, E, B. Okay. Now you can pause the video. You can pause the video, practice that. Okay. Find all these terms with the correct signs. Then you're going to compare your equation with the equation I got. Okay. As a practice, good practice. All right. So now let's see. I start from B. I start walking. I see this guy. I see this guy. How do I write down the voltage? I2, 8 ohms, right? What is the sign? Current going this way, and I decide to travel clockwise. So when I cross this resistor, I'm traveling with the current, negative. Okay. Now keep walking. Now I see this battery. When I see a battery, forget about the current. Write down the voltage, and then are you going from negative to positive or positive to negative? I'm going from negative to positive, right? Because I'm traveling this way. So I'm climbing up. I'm gaining some potential when I cross this battery. Plus. Okay? Now keep walking. Now I see this 0.5 ohm resistor. So the current is still I2, right? Remember this whole path, this is one path, has the same current I2. So I'm going to write down I2 times 0.5. All right? What is the sign? I'm still traveling with the current. I'm going downhill. Okay, negative. Now keep walking. Now I see this 0.75 ohm resistor. The current is still I2. So the voltage I write is going to be I2 0.75 ohm. Right? What is the direction? Or what is the sign? Well, I'm still traveling with the current. I'm going downhill with water. My potential goes down. I need a negative sign. Keep walking. Now I see a battery. Okay, forget about this current. I'm going from positive terminal to negative terminal. I'm going downhill. When I cross this battery, that's going to be negative 24 volts. Okay, now keep walking. Now I'm going to go up, right? Because I want to finish this loop. I see this resistor, 0.25. So the voltage is going to be I3. Now the current becomes a different current. Right? And then what is the sign? Now you see that I'm going against the current. I'm going up here. I'm climbing up. I'm going against the water. I'm climbing up. I'm going uphill. Positive. Now I see a battery. Okay, when I see a battery, forget about the current. Take a look at these two lines. If I'm still traveling clockwise, I actually go from positive to negative terminal. Okay, I'm going from higher potential to lower potential. My potential decreases. I lose potential. Now keep walking. Now I see this 6 ohm resistor. Okay, the current is still I3. I'm going to write I3 times 6. And then what is the sign? I'm traveling against the current. The current flows downhill this way. I'm traveling opposite to the direction. I'm climbing up, positive. Okay, then I'm back to B, 0. 3 equations, 3 unknowns. You can always solve them. It's like you have 3 equations with X, Y, and Z. How do you solve 3 equations for 3 unknowns? You substitute and substitute, right? You're going to find the expressions for like 2 different unknowns. Plug them into the third equation. You will get, at the end, you will get a one equation for only one unknown. Solve that equation, you get that unknown, then you go backwards, you can solve the other two. That's how you do that, right? That's how you solve a bunch of equations for a bunch of unknowns, okay? So the first thing I would do is this. I'm going to simplify the equation 2 and equation 3, right? This guy, there's no way you can simplify it, but you can rearrange it, say, get an expression for I1. If I want to solve for I2 or I3 first, right? And then I'm going to simplify this. I'm going to put all these I1s together, I3s together, right? So the second equation, at least I can first simplify. So it's going to be this. It's going to become an equation like this. I1 and I3, okay. Equals a number, right? And then I can simplify the third equation. It's going to be a number times I2 plus a number times I3 equals a number, right? And then you go ahead and use all these three equations. So the first equation is I1 minus I2 minus I3 equals 0, right? And then you solve these three equations, right? So you can decide if you want to solve for I2 first, you're going to use two of its equations to write I1 in terms of I2. Use another equation to write I3 in terms of I2. And then put everything together, and then you get an equation for I2 only, solve for that. Okay? So the algebra is going to take you some time to finish. Of course, you're not going to finish this like in 5 minutes. It's going to take you some time. So now you can pause the video, see if you can finish the algebra, okay? And that's when people make mistakes, okay, especially on a test, okay? It's not because they don't know how to do that. They always make stupid, silly or careless mistakes when they rearrange these equations. So definitely you want to be extremely careful when you solve a problem, when you solve a circuit like this using Kirchhoff's rules. It's all about the algebra. It's all about the algebra. Okay, so let's see. When you put everything together in this equation, okay, combine them. So what I get is this. I get negative 35.5 I1, and then negative 6.25 for I3, and then equals a number negative 21, okay? And the third equation, I put all the terms together, I get negative 9.25 I2 plus 6.25 I3, and then equals 15, okay? Okay, I'm just solving for I2, I1. Now you see that, okay, so how do I solve that? So let's see, how did I do that? So I actually solved for I1 first. Okay, I solved for I1 first. So the first thing I did is this. I used this equation to find expression of I3, right? So you move this term to right and divide both sides by negative 6.5. So what is the expression I got for I3? I3 equals 3.36 minus 5.68 I1. So that's what I got, okay? And then what I did here is this. I used this equation to write I2 as I1 minus I3. There are different ways to solve them, totally depending on which one you want to solve first, right? And then I'm gonna plug this into this equation, okay? So what do I get? So I'm gonna substitute I2 with this. So I get negative 9.25 I1 minus I3 plus 6.25 I3 equals 15, right? Then I'm going to distribute this and then put these I3s together. So what do I get? So I would get negative 9.25 I1. I would get positive 9.25 I3 plus 6.25 I3 equals 15, right? You put this together. So I would, oh, and then you see that, put these two numbers together, I get 15.5 I3 equals 15. Now I'm going to plug in this I3 into this equation I got. right? So I would get negative 9.25 I1 plus 15.5 3.36 minus 5.68 I1. This whole thing equals 15. Now you see that this equation only has I1 in it, because I did substitution and substitution, right? Now you distribute this, you put all the I1s together, all the numbers together, what do you get? At the end, I get this, negative 97.29 I1 equals negative 37.08. Okay, now you can divide both sides to get I1. I1 0.38 amps, right? Now once you find I1, you can go back, use this equation to find I3, okay? So I3, you plug this number in, you get 1.20 amps. Now you can go back and use this equation, I2 equals I1 minus I3. Okay, so I2 equals I1 minus I3, you get negative 0.82 amps. Now, okay, what is this negative I2? Did I do something wrong? Okay, no, you didn't do anything wrong, because take a look at this diagram. The problem says that, okay, I1 goes this way, I2 goes this way, I3 goes there. But is that really right? Okay, because there's so many batteries here, right? So this battery tries to drive a current this way. This battery tries to drive a current this way. But what about these two batteries, right? See, this battery wants to drive a current this way, okay? But this battery wants to drive a current that way. So you can, if you have a very complicated circuit, you cannot predict the direction of each current, okay? So what you can do is this. Even if the problem doesn't tell you the direction of the current, even the problem just says, find the three currents in this circuit, and you see that there are only three currents in this circuit, right? It looks complicated, but you only have three currents here. You can pick any direction you like, okay? I can say I1 goes this way, I2 goes this way, and I3 goes this way, or the other way around. You can pick a random direction for I1, I2, I3. You do the algebra, okay? You finish everything correctly. If the answer you got is positive, that means your assumption for I1 is right. I1 is going in the direction as you assumed. You get I3 positive. I3, it's gonna be in the direction you assumed, okay, right? You get I2 negative. Okay, that means your assumption was wrong, but you don't need to do all the algebra again, okay? All you need to do is just make a note at the end. I2 actually goes opposite to the direction I assumed, okay? So the right direction for I2, I3, I1 is going to do this. I1 actually goes this way, right? I3 goes this way, right? But I2 actually goes this way. And I don't need to figure them out before I set up these three equations, because there's no way I can figure them out when there are so many batteries here. And you don't even need to take a look at these batteries. Oh, these batteries are fighting, okay? This battery tries to go drive a current this way, the other battery tries to drive a current that way, and there's a third battery. Do I compare the numbers to determine at the end which one is going to win? You don't, okay? You don't. You just assume some random directions from at the beginning. You stick to the directions assumed. Set up this equation, because this equation, the signs of each term depend on the direction of the currents you assumed, right? Okay, you set up these three equations, you do the algebra, you solve for these three currents. At the end, the signs are going to tell you the right direction of this current, okay? That's the beauty of this theory, right? You don't even need to figure out anything, okay, in the first place. Do the math. The math is going to tell you everything, okay? The math is going to tell you everything, okay? So that's the Kirchhoff's rules. So we have finished Kirchhoff's rules. So now we have pretty much finished the electric field, okay? So starting next time, we're going to start the discussion on magnetic fields, okay? So magnetic fields, so now we can move on to the next PowerPoint 11, okay? Magnetic field, well, I'm sure that you have seen magnets yourself, right? Magnets always has a north and south poles, right? And then we know that the interactions between the north and south pole are the same to the electric charges, okay? Like poles repel, unlike poles attract, okay? So that's why these compasses, they will respond to a magnet, right? If you have a compass, right? Because the compass is just a very small magnet, okay? So in this case, you see that. So this must be, if this is a north, okay? So if it attracts this end, so this end is the south, okay? So the other end is going to be attracted to south. So this end is north, right? So I'm sure that everyone has played with these magnets, okay? Okay, so that's what we're going to study now. And then another thing is this, right? So these magnets, they can also attract other things, not just magnets. They can also attract paper clips, right? If you try that. Do I have any paper clips here? Yes, I do. So they can attract the paper clips, right? So there are certain materials they can be attracted to a magnet, and they're called ferromagnetic materials, or just magnetic materials. Okay, the most common magnet materials is the iron, right? I'm sure everyone knows that. That's why you can put the fridge magnet on your fridge, right? Okay. So you see that interactions between these poles are very almost the same as the electric forces. So that's already a hint that electric force and the magnetic force must be connected, okay? And you see that electric charge has positive and negative. Magnetic poles has north and south. Well, you could call them positive and negative if you like, right? But we just call them like north and south, okay? But there's a big difference between magnetic force and electric force. Because for electric force, we do have isolated, okay, positive charge and negative charge, right? Free negative charge, free positive charge. A proton carries positive charge, an electron carries negative charge, right? But if you cut a magnet in half, okay, you don't get a south, you don't get a north, you still get a complete. You get two complete magnets with south and north, okay? And if you do that one more time, you get 4 complete magnets, north and north, north and south, okay? So you can keep doing that, okay? And you never get a single isolated north pole or single isolated south pole. So they're called magnetic monopoles. And it turns out, in nature, they don't exist. Okay, so that's a big difference from electric charges and electric forces, right? So why is there electric positive and negative electric charges isolated, but there's no isolated north or south pole? Okay, that's still a very big mystery in nature. We still don't know the answer, okay? But all the evidence we have now, okay, strongly, okay, favors that there's no isolated north or south poles or magnetic monopoles, okay? So there's still physicists working on that, okay? They're trying to find magnetic monopoles. They're trying to make magnetic monopoles, okay? Because if anyone discovers magnetic monopoles, a single north or single south, even in like a microscopic scale, okay, it's got to be a Nobel Prize, and it's gonna it's gonna rewrite the theory for E&M we have now. So it's gonna be a huge discovery, okay? If you have seen the Big Bang Theory, okay, the TV show, okay, and then in one of the episodes, in early seasons, very early seasons, okay, first of all, if you have seen the Big Bang Theory, if you haven't, okay, you do need to see that, okay, okay. So it's my favorite, because it's about physicists, of course, right? Sheldon Cooper, right, always think he's the smartest person in the world. What does Sheldon Cooper study, if you have noticed? He studies string theory. String theory is a very, very complicated theory, but a lot of people who study string theory think that that's the most favorable candidate for the ultimate complete theory of everything. Remember I said physicists always believe there's a complete theory in this universe. It's just we found like different pieces here and there. Okay, at the end we should be able to put everything in a complete theory. So string theory aims for that. Okay, but string theory is really complicated, and we still don't have all the details for string theory. So there are a lot of people who like them. Okay, so they're working on that. So in that TV show, Sheldon Cooper studied string theory. So that's why he thinks he's the smartest person in the world, right? Because string theory is really complicated. So there are also people, okay, against the string theory, okay? One of the criticism string theory always receives is that string theory predicts the existence of magnetic monopoles, okay? So that's actually one way to prove string theory is true, right? If you have a theory and then you want me to believe that theory, right? You're not going to tell me some experiment I can do in order to confirm your theory, so I can believe that. So one of the predictions, you need to make some testable predictions, so I can set up experiments to confirm that, right? So one of the predictions made by string theory is that existence of magnetic monopoles, okay? But so far, we haven't found magnetic monopoles. So that's one of the reasons. There are also a lot of people, okay, there are two extremes, okay? There are also people against string theory, okay? So in one of these episodes, I believe is season 2, episode 23, okay? If you can find it, watch it. So Sheldon Cooper gets the opportunity to go to the North Pole, okay, to do experiments to detect the slow-moving magnetic monopoles, okay? The reason? Because he studied string theory, and he really wants to find magnetic monopoles, right? If he can find magnetic monopoles, that's got to be a Nobel Prize, okay? And that's going to be a big triumph for string theory, right? So of course, they don't find the magnetic monopoles in that experiment. But on the next episode, which is actually the episode 1 of season 3, okay, they come back, they spend a few months there, they come back, and then so Sheldon Cooper actually thinks that he has discovered the magnetic monopoles, but it turns out his friends, in order to make him happy, they have faked the data, okay? So in that experiment, they didn't discover any magnetic monopoles, which is true, right? Because so far, we still don't have any evidence for magnetic monopoles, right? There's still physicists doing experiments and theories in order trying to find that, okay? But anyway, his friends, okay, in order to make him happy, okay, they have faked the data, okay, so that he believes that he has found the magnetic monopoles, okay? And then, of course, they tell him the truth, so he gets really upset, okay? So if you have time, you can find these 2 episodes, okay? the episode 23 of season 2 and the first episode of season 3. Okay, very funny to watch. Okay, but anyway, that's the magnetic monopoles. We don't have magnetic monopoles. That's a big difference between electric field, electric force, electric charges, and magnetic field. Okay, but other than that, there are a lot of similarities between them. So there are already a lot of hints. They must be connected. And as we're going to see at the end of the semester, you can unify these two fields in one complete theory, what we call Maxwell equations. Okay, so we're going to continue this discussion next time.